introduce the next speaker for today is Ole Burghardt of the Group of Scientific Computing at TU Kaiserslautern in Germany. The floor is yours. If you can, please turn on your webcam.
Thanks, Piero. Can you hear me?
Yes.
Okay, perfect. I can't see any button to turn on my camera, so I guess I would just directly go ahead.
Yeah,
just go ahead, Ole. You cannot use your webcam from the Linux.
All right. Okay. So, yeah, hello everyone, and welcome to this short introduction to the native discrete adjoint multiphysics solver in SU2. To start off with, so please go to the first slide, please. To start off with, let's first have a look on some standard multiphysics problems. What SU2 natively supporting is, for example, fluid structure interaction, where some elastic solid like an airfoil deforms under aerodynamic forces, or conjugate heat transfer, where heat is transferred from or into a heat conducting solid to some other physical domain like a fluid flow. And but beside these two prominent examples, one could of course as well think of all sorts of other couplings, or as we see it on the right, combinations of already existing ones, like we see it here. It's a cool turbine blade that would also deform under forces in some high temperature compressible flow. Next slide, please. Yeah, generally speaking, what most multiphysics problems that SU2 currently supports have in common is that it couples different kinds of physical zones through exchanging data at common physical boundaries during the simulation. Like in case of FSI, the flow solver transfers flow directions to the elasticity solver, and then the elasticity solver returns boundary displacements. Or next, please. In case of CHD, the flow solver transfers heat fluxes to the heat solver, and then the heat solver would return temperature distributions. Yeah, and so on and so on. However, for the scope of this talk, the concrete choice of the physical setup is actually not important, but the message here is just that all solvers can possibly depend on solution variables of all other solvers. So in order to see what I mean by that, let's slowly move to the multiphysics adjoint computation. But first of all, let's see how to run them. So a multiphysics simulation SU2 is based on creating a what we call master config file with the solver set to multiphysics, and where we reference all the usual configuration files through the option config list. And the crucial difference here, so the crucial difference between the master config file and the usual ones, is that in the master config file, we define interfaces where no boundary conditions are prescribed, but where solvers are coupled. So yeah, and let me also point you to last year's presentation by Tobias, how to set up multi-zone problems in SU2, that can be found on the SU2 Foundation website. Next, please. So yeah, after having defined an objective function in your master configuration file, SU2 can also compute fully coupled adjoint solutions just by running SU2 CFD-AD. That would then capture and include all dependencies between the primal solvers that would then later result in cross derivatives. And what this last sentence hints to is that it's intuitively clear that if a coupling was included to the primal simulation, this must be somehow reflected in the adjoint computation. And it's clear that the multiphysics adjoint solution won't just be the concatenation of individual zone-wise adjoint solutions. But before we take a closer look at this, let us shortly recapitulate some notation and how we can use adjoints for sensitivity analysis. So yeah, let X be a vector of design parameters, UK the variables of the solver in zone K, GK the flow solver in zone K that we assume to be a fixed point solver, and lambda K the adjoint solution for a given objective function. And then the gradient of J with respect to X can be represented by this formula here. And we see that using the adjoint, there are no terms d over dx of u, so no derivatives of the converged flow solution with respect to the design parameters, which would have been very costly and which one would have expected from naively applying the chain rule to jx u of x. So yeah, that's a very handy thing. And the formula to compute the adjoint is given here already in its precise formulation for multiphysics problems, showing that if a solver in zone K has had some influence on the solver in zone J during the primal simulation, the adjoint solution in zone J then adds to the adjoint solution in zone K by amounts of this cross derivative written down there. Right. Yeah, our implementation of the discrete adjoint multiphysics solver is pretty much just based on that formula, and it's foremost based on a careful distinction between cross terms. So those are the terms in the sum of solution operator derivatives for J not equal to K, and diagonal terms, which would be the usual term the discrete adjoint solver in each zone is built on. Yeah, blah blah. Allow for a generic approach, and that is also adaptable to multiple kinds of partitioned multiphysics problems. And more precisely, it is built upon routines for updating the adjoint solution in a zone K for inner eta times, with all coupling terms being fixed. And that would require that we somehow store these coupling terms, because keeping them fixed does not mean that we exclude them. So yeah, we store them in some external data structure. And once we've obtained a new adjoint solution in a specific zone, we update all the coupling terms before switching to zone K+1. And note the change of indices here in this is in this fraction. So for obtaining lambda K, we need all the other adjoint solutions, and once we've obtained it, we must update the cross terms for all other zones. And yeah, then the algorithm is closed by an outer loop across all zones for outer eta times. Yeah, so that's what I wanted to say on multiphysics adjoints and on our implementation. And for the rest of this talk, let's apply this to some test case. This one's for simultaneous CHT and FSI, consisting of one fluid zone and 3 elastic heated solid zones. Yeah, as for the setup, so next please, next slide. We have one fluid zone that is shown here. Then we have the 3 elastic deformation zones or solid zones. So next slides as well, please. And then we overlay these 3 elastic zones by heat conducting zones that will then deform in the very same way as the other zones through 3 extra FSI interfaces, but which will also transfer heat into the fluid flow. And all credits at this point to Petru for his idea to realize aerothermal elastic simulations in SU2 this way. And once we've run the simulation, our objective function will be the integrated heat flux at all outer parameters of the solid cylinders. So yeah, in total, we have our simulation is built. Our simulation consists of 7 simulation zones with different associated solvers, and 6 FSI interfaces, 3 CHT interfaces. And then let's now look at the simulation results. So that's the temperature distribution that's most interesting for us, as our objective function is the integrated heat flux. And what you can also see that the first cylinder is slightly deformed. That's shown in this plot here. So in the previous slide, you can already see that's slightly deformed, and in this one, you can more precisely see that the FSI effect is really included. Yeah. So now we are running the Discrete Adjoint Multiphysics solver just by SU2 CFD AD. And then we will validate our coupled adjoint solution through validation of mesh sensitivities against finite differences through a single FFD box parameter. Yeah, that's just one FFD parameter here shown in the FFD box. Yeah, so for the simultaneous problem, the finite differences converge nicely. Although there remains a slight error to the AD-based one, and though taking out the deformation part of the simulation, so as for a pure CHD problem, the error almost vanishes. Yeah, and to conclude, next slide, please. For the fully coupled problem, a relative error of 3.2% is achieved, and for the same problem, including no deformation, the relative error reaches, okay, it almost vanishes. And yeah, a small error for the fully coupled problem can arise from memory saving simplifications for interpolation operators and for mesh deformation. That's in particular the case for FSI couplings. And yeah, this test case or the CHD version of this test case can be found on our GitHub page. I will also add this one, including the deformation part, just right after the conference. And yeah, that's all I wanted to say. Thanks for your attention, and maybe there's now time for 2 minutes time for some questions.
Thank you very much, Ole. A very exciting advancement also in this aspect of multiphysics. I have a question for you. Do you already have in mind a more applicative case, a more real-life case? Are you engaged in some project that provides this kind of cases?
Not yet. So a more demanding case would be, for instance, this cool turbine blade, though it's also a more academic case, I would say. And as for a real industrial application, yeah, I'm looking forward to soon apply it to some, but not yet. That would be the answer.
Sure, and I am sure here in the community there are quite a number of people.
Though I have to add that the WB7 heat exchanger that you've seen in the introductory slide, that's something we are working on together with some colleagues at Bosch, and maybe I mean the multiphysics discrete adjoint solver is used for computing the derivatives. So I mean it's used, the multiphysics discrete adjoint solver, but as for a combined use of this multiphysics discrete adjoint solver, that's not yet. There's no industrial application case yet.
Thank you, Ole.